In this short video, I'd like to talk about 5 big questions about the universe and hopefully provide you with the answers. The 5 big questions are: how did the universe begin? What is the universe made of? What rules does the universe follow? What are dark matter and dark energy? And finally, how will the universe end? So the first big question then, how did the universe begin? Well, the universe began in an event referred to as the Hot Big Bang about 13.8 billion years ago. This instant marked the creation of time and space has expanded and the universe has cooled as time has progressed ever since. The expansion of the universe was first noted by Edwin Hubble in the 1920s, when he observed that the more distant a galaxy was, the faster it appeared to be receding from us, measured by its redshift. The cooling of the universe was demonstrated by Arno Penzias and Robert Wilson in the 1960s, when they observed that the whole sky glows in the microwave region of the electromagnetic spectrum, with a distribution that's characteristic of a temperature of just 3 degrees above absolute zero. The early universe was initially very hot and dense and contained almost equal amounts of matter and antimatter in the form of quarks and antiquarks. There was an imbalance of about 1 part per billion in favor of matter. So when the matter and antimatter particles annihilated each other, producing photons, in the first fraction of a second after the Big Bang, just 1 matter particle remained for every billion photons. The remaining quarks combined to form equal numbers of protons and neutrons, but then neutrons decayed over the next few minutes until protons outnumbered neutrons by about 7 to 1. Atoms then formed as the universe cooled further and began to clump together under gravity, forming the seeds from which clusters of galaxies later grew. About 300,000 years later, the photons reacted with atoms for the last time and are visible today as a background glow across the universe, redshifted into the microwave part of the spectrum. The second question then, what is the universe made of? Broadly speaking, the universe is made of 5 different types of stuff. Firstly, baryons, heavy particles, that's protons and neutrons, which are made from quarks and which form the nuclei of all atoms. The second type of particle is leptons, or light particles, that's electrons and neutrinos. I'll say a bit more about those later. Next, there is dark matter and dark energy. We don't know what these are, but I'll say something about those later too. And finally, the 5th type of stuff in the universe is photons, that's electromagnetic radiation. So the visible universe on the largest scales takes the form of a structure known as the cosmic web, comprising vast sheets and filaments separated by voids and containing clusters and superclusters of galaxies. Each galaxy may contain up to hundreds of billions of stars, along with clouds of gas and dust. Each star may be surrounded by its own family of planets, moons, asteroids, and comets, which in turn were created from the debris left behind after the star itself formed. This visible matter is mainly hydrogen, that's about 74%, and helium, about 25%, with only small amounts of other elements, chiefly oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur. These are referred to by astronomers as metals. It was only in the 1920s that astronomer Cecilia Payne-Gaposchkin was the first person to realize that stars are composed almost entirely of hydrogen and helium. The heavier elements are all formed by nuclear fusion reactions inside stars and then dispersed into space when they die. At a deeper level, atoms comprise a tiny nucleus made of positively charged protons and electrically neutral neutrons, surrounded by a cloud of negatively charged electrons. Protons and neutrons are composed of triplets of up quarks and down quarks, and ghostly particles known as neutrinos are also present in equal numbers to the protons and electrons. They pervade the entire universe, but rarely interact with it. Electromagnetic radiation in the form of 1 billion photons per proton is present throughout space as radio waves, microwaves, infrared, visible, and ultraviolet light, X-rays, and gamma rays. However, less than 1% of the total mass and energy of the universe is observable in this form, but another 4% is present as invisible baryonic matter, also made of atoms, but in the form of massive compact halo objects, that's machos, dead stars in the outer regions of galaxies, and the warm hot intergalactic medium, or WIM, that's invisible gas in the regions between galaxies. The remainder of the universe comprises non-baryonic dark matter and dark energy, the natures of which are currently unknown. So what rules does the universe follow? Well, there are four fundamental interactions that underlie all processes in the universe: the gravitational, strong, weak, and electromagnetic forces. Gravitational forces act between all particles with mass. Strong forces act between any particles with color charge. Weak forces allow particles to change into other particles. And finally, electromagnetic force acts between any particles with electrical charge. So on the largest scales, Albert Einstein's general relativity is a theory of gravity that describes interactions between any objects that possess mass. It's encapsulated by the phrase, space-time tells matter how to move, and matter tells space-time how to curve. Accelerating massive objects emit gravitational waves that travel at the speed of light. On small scales, interactions are described by theories of quantum physics, which have two key features. First, matter and radiation interact by emitting or absorbing quantized amounts of energy. And secondly, the positions and speeds of particles are intrinsically indeterminate when investigated precisely. They also embody the concept of wave-particle duality, which says that matter and radiation interact as if they're composed of particles, but move through space as if they're a wave. The strong interaction is described by the theory of quantum chromodynamics, or QCD. Quarks possess a quantity known as color charge, which comes in three varieties: red, green, and blue. They emit and absorb gluons, enabling them to bind together into color-neutral composite particles, such as protons and neutrons. A leftover strong interaction allows protons and neutrons to bind together to form atomic nuclei. The weak interaction allows quarks and leptons to change from one to another, mediated by the emission and absorption of W and Z bosons. Electric forces and fields exist between static electrically charged particles, while magnetic forces and fields exist between moving electrically charged particles, that's electric currents. A changing electrical field induces a magnetic field, and a changing magnetic field induces an electrical field. These effects were synthesized by James Clerk Maxwell in the 1860s to show that light is an electromagnetic wave. The electromagnetic interaction is now described by the theory of quantum electrodynamics, or QED, which envisages the exchange of photons carrying specific quanta of energy. The next question then is, what are dark matter and dark energy? By studying the tiny fluctuations in the structure of the cosmic microwave background radiation across the sky, we can infer that non-baryonic dark matter constitutes about 26%, and dark energy constitutes about 69% of the current mass energy of the universe. Dark matter is so called because it doesn't emit, reflect, or absorb electromagnetic radiation, and so its presence can only be inferred by the gravitational influence it has on other things. In the 1930s, Fritz Zwicky first suggested its existence by studying the motions of galaxies in the outer regions of galaxy clusters. Then, in the 1970s, Vera Rubin found a similar effect studying the motions of stars in the outer regions of spiral galaxies. In both cases, the rapid speeds observed implied that more matter must be present than is observed. Now, dark matter cannot be made of normal baryonic matter, protons and neutrons, and various suggestions for what it is have been proposed, but none are confirmed. Two suggestions are particles called axions and weakly interacting massive particles, or WIMPs, but neither are observed directly. In the late 1990s, astronomers studying distant supernovae, that's exploding stars, noted that they were fainter than they ought to be if the universe had been expanding at a constant rate since the Big Bang. This implied that light has traveled a greater distance to reach us than otherwise inferred. The explanation is that the expansion of the universe has speeded up in the last few billion years, and so the expansion of the universe is currently accelerating rather than decelerating, as would be expected if it contained only matter. This suggests the existence of a force which opposes the gravitational attraction of matter and has been attributed to something called dark energy. The nature of dark energy is currently unknown, but unlike matter, it does not become more diluted as space expands. So on to the final question, how will the universe end? Well, if the universe were composed only of matter and radiation, then it could either expand forever, or its expansion could eventually reverse, leading to a big crunch at some time in the future. The dividing line between the two outcomes depends on the amount of matter and energy present in the universe. A low-density universe would expand forever, while a high-density universe may eventually collapse. Although the overall density of mass energy in the universe is now known to be extremely close to the critical dividing line between the two scenarios, the story is confounded by the existence of dark energy. Since dark energy accelerates the expansion of the universe, it can never collapse. But there are nonetheless two possible scenarios determined by the equation of state parameter for dark energy. If this parameter is small, galaxies will attain an infinite distance apart at an infinite time in the future. All the stars would eventually run out of nuclear fuel and evolve into white dwarfs, neutron stars, or black holes, which would then spiral in to be swallowed by the supermassive black holes in the centers of galaxies. Given enough time, black holes will evaporate into a swarm of matter and antimatter particles, which in turn would annihilate each other, creating electromagnetic radiation. The ultimate fate of such a universe is therefore a dilute sea of cooling photons called a heat death. Alternatively, if the parameter is large, the density of dark energy will continue to increase as the universe expands, and the accelerated expansion will proceed ever more rapidly, eventually tearing the universe apart in an event called a Big Rip. In this case, not only would galaxies become disrupted as gravity is too weak to hold them together, but also planetary systems, stars, planets, and ultimately even atoms would be destroyed until space-time itself is torn apart, marking the end of the universe. And that's the end of my 5 big questions.